Hello viewers, welcome to this session. In this session we will introduce the solution of Volta integral equation of second kind. This is the second kind Volta integral equation, and phi of x equal to f of x plus lambda 0 to x. This is the resolvent kernel depend on lambda, so this is the infinite series of lambda. So written style is this same, and f of xi, this is the known function. So this is the solution of the integral equation. We prove it where the resolvent kernel produced from the kernel or iterated kernel. So let's go please. So we will prove that this is the solution of this integral equation where resolvent kernels is this. For proving this or determine the solution of an integral equation in the form of infinite series, so we say infinite series solution, that means phi naught x plus lambda phi 1x plus lambda square phi 2x, and the nth term of this phi n of nx. This is the infinite series. This is the solution of number one equation. That means this equation, if we putting this solution in the left side and right side and equating the coefficient of lambda, so we get some relation, and from this relation we find the phi naught and phi 1x and phi 2x, and putting these values of this, then we find the real solution. So now we replace the value of phi x. So if we replace the values of phi x, the left hand side is this and the right hand side is f of x plus lambda 0 to x kernel x comma xi, and phi of xi, that means phi naught xi plus lambda phi on xi plus lambda square phi 2 xi, and this is the infinite series, and the integrating variable is xi. So now equating the coefficient of like power of lambda, we get this is the coefficient of power lambda naught, that means we constant terms, and these are the constants in terms of lambda. So we will write phi naught x equal to f of x, and similarly phi 1x, this is the another coefficient of lambda, and from the right sides the coefficient of lambda equal to 0 to x kernel x comma xi phi naught of xi dxi. If we equating the coefficient of all, then we get some relation. So next relation phi 2x equal to 0 to x, and lambda square coefficient, that means kernel x comma xi and phi 1 xi dxi. So now I will write the all findings. Means phi naught of x equal to f of x and phi 1 of x equal to integration 0 to x kernel x comma xi phi naught of x xi dxi, and phi 2x equal to 0 to x kernel x comma xi phi 1 xi dxi. So phi n of x equal to 0 to x kernel x comma xi phi of n minus 1 xi dxi, and this is the infinite series also. So if we using the results, then this method is called the iterated function methods. because we find a function, and using this function we get another function, and using this function in here we find the another functions. This iterated function will be results. So using this we find the resolvent kernel and putting the resolvent kernels in the solution, and we get a real solution. We see this in the example, but we firstly we read another example that will be the real methods with iterated kernel. That means what is the iterated kernel in here? Iterated kernel, that means this is not, this is iterated function, but we use a iterated kernel method. That means kernel is produced from kernel, but function is unsensed in here. So if we use this method, firstly we prove the theorem. So if we write the phi 2x in terms of phi on x, then we will see that phi 2x equal to kernel 0 to x and limit is 0 to x, and kernel x comma xi, and the putting the values of phi 1 xi and putting the values of 0 to xi, kernel xi comma xi1 because when we replaced x by xi, then two xi are mixing, so xi is replaced by xi1 firstly, and then x is replaced by xi. That means phi of xi1 d of xi1 and dxi. So firstly we integrate this and finding results, and second time we integrate with xi, then we find this iterated function. So in these methods we solve it with the using the example. But if we formulate this such as way, this interchanging the order of integration, that means first we integrate with dxi, that means integrate with xi, and second time we integrate with xi1. So what represent from this? Firstly we will define the integrating area, so domain. That means if we draw a curve, that is xi1 and this is xi. So if we write this, this is origin. From this we can write this is xi equal to 0, this is xi equal to x, and this is xi1 equal to 0, and this is xi1 equal to xi. So what is the relation in here? Xi equal to 0, that means xi equal to 0 in here, and xi1 equal to 0 in here. So this is the line, this is the xi1, and xi equal to x, and here xi equal to x, that means xi equal to x, and here xi1 equal to xi, that means this is the straight line which passes through the origin and makes an angle with xi1 and xi both 45-degree angles. So this is the xi1 equal to xi. So these four lines produce a area. This integral domain is this. If we write the interchanging order of integration, so it can be written as 0 to, firstly we integrate with xi. So the limit of xi is, this is the upper limit and this is the lower limit. So if we integrate with xi, this is the lower limit and this is the upper limit. So lower limit of xi equal to xi1 and xi equal to x. So the this is the xi1 and this is x. The limit of xi, that means dxi, and kernel x comma xi and kernel xi comma xi1, and ape of xi1, because the ape of xi1 is constant when we integrate with xi. Then this is written in the outside of this integral. So the limit of xi1 limit, this is the limit of xi1, that means xi1 equal to 0, and this is the another limit. So another limit is xi equal to x and xi1 equal to xi. So xi1 equal to x in here. So 0 to x, the integrating limit in here. So this integral can be written in this form, so using the interchanging the order of integration. If this can be written as the iterated kernel, that means these two are produced from the kernel. So if we write this as this way, that means if we write this k2, so equal to 0 to x ape of xi, and this equal to can be written at x k2 x comma xi1, because the limit is xi1 and x, so function is defined x comma xi1, and this is the integrating variable in here xi1. So where k2 equal to this, so this is the k2 x comma xi. If we rewrite the general terms of the general term, that means phi n x, so what is the general terms? It is the phi 2x. So when phi n of x, what can be written? That means ape of xi is unsensed. Ape of xi1, this is unsensed, and this will be generated new. So it called be iterated kernel, where first kernel can be called kernel k1. That means we can write kernel x comma xi equal to k1 xi1. So first iterated kernel, that is the same of iterated kernel, that was defined by recursive relation. So this recursive relation can be defined from this. We write this recursive relation before. So I will write the general terms of phi x, and after then we write the recursion relation of kernel from here. So first we write a general terms, that means phi n of x. What is phi n of x? That means phi n of x 0 to x kernel kn x comma xi and f of xi dxi. These are the general terms. Please see in this, here the integrating variable is lambda. For that reason there is a lambda, sorry, integrating variable is lambda 1, so there is a lambda 1 and lambda 1. When we write this is lambda, so these are convert to a lambda. In this sense it can be written. And the recursion relation, that means kernel k1 plus 1 equal to that is the function of x comma xi, but this kernel is the x comma xi1. So x comma xi, what can be written? that means xi comma 2x. Here you see that this is the xi1 and this is xi, sorry, x, and this is the x2 xi to x, and kernel x comma z, that's the another variable we use in here. This is the z, this is the z, this is the z, because we write the z on to z, for that reason. So we will define z in terms of xi. So kernel of z comma xi and dz. So this is the general form of iterated kernel, and this is the general terms of iterated function, that means n function. So now I will write this in the function, given function. So what's we find? Phi x equal to f of x plus putting the nth terms and using the summation n equal to 1 to infinite and lambda to the power n and integration kernel n x comma xi f of xi dxi and 0 to x the limit, where the resolvent kernels x comma xi lambda equal to k1 x comma xi plus lambda k2 x comma xi and lambda square k3 x comma xi, and in summation convention, that means n equal to 0 to infinite lambda to the power n and kernel n plus 1 x comma xi. When the putting the values of n in here, then we find this series. If this series can be written as these forms, that means using this lambda n equal to 1, then this can be written as lambda to the power n minus 1 and k n x comma xi. These two are same, but written form is different. When we start n equal to 1, then we can write it. So if we common a lambda from in here, then it can be written as lambda n minus 1. So this is can be written as the resolvent kernel. So the solution can be written as these forms. That means phi of x equal to f of x plus lambda 0 to x resolvent kernel x comma xi lambda and f of xi dxi. So this is the solution of the given integral equation, Volta second kind equation. Now I will discuss the solution using the iterated function and using iterated kernel. So we use a very simple equation to solve it. For time consumption, phi of x equal to 1 plus 0 to x phi of xi d of xi. This is the integral equation. If we consider the solution, phi of x equal to phi naught x plus lambda phi 1x and lambda square phi 2x, and as soon as then we will consider, and this is the solution, and putting this in here and equating the coefficient of lambda, then we find a phi naught of x equal to f of x, and here f of x is 1 and phi 1 of x equal to 0 to x. Kernel, here is kernel is 1 also, and phi naught of x, that means phi naught of x, that means 1, and dxi. So integrating from this, and we get the solution is x. Phi 2x equal to 0 to x, and kernel, that is 1, and phi 1 of xi, that means this is xi dxi. So solution xi square divided to the upper limit and lower limit is 0 to x, and putting this value, this is the x square by 2. And if we find the phi 3 of x, then 0 to x, and phi 2 xi, that means xi square by 2 dxi, and from this we get xi cube by factorial 3. And putting the values of a phi naught, phi 1, phi 2 in this here, and values of lambda is 1, so we find the solution phi of x equal to 1 plus x square divided 2 and x cube by factorial 3. So this is can be written as factorial, and everyone knows it, this is e to the power x. So e to the power x be a solution of this integral equation. Now I will find the resolvent kernel when the kernel is 1. So when the kernel x comma xi equal to 1, then we know that first kernel equal to x comma x equal to 1, that is the same by the iterated kernel, that means k of xi equal to xi to x, and k x comma z, and k z comma xi, and dz. So xi to x, kernel x comma z, kernel x comma z, that means 1, and z comma xi, that is 1, so dz, and this is x minus xi. So easy. And when we putting this k3 xi, so the kernel here we use this is 1, and the next k2, this will be written as kernel xi to x k x z, and k to z comma xi dz, and putting in here. So we, and integrating this, we find that, so k x comma xi, that is the value of is 1, and this the value of is when x comma xi, then x minus xi, so z minus xi, this is the value is z minus xi dz, and integrating this, and we get and find the values from here, that is x minus xi whole square by factorial 2. If we find k4 x comma xi, probably this answer x minus xi to the power cube by 3 factorial. And using this, we get an iterated kernel, we get this iterated kernel, and from using the iterated kernel we find the resolvent kernel, that means resolvent kernel r of x comma xi comma lambda equal to summation b equal to 0 to infinite, that means n equal to 0 to infinite, we can write it lambda to the power n, and k n plus 1, and x comma xi. Putting this here the iterated kernel, and we get n equal to 0 to infinite lambda to the power n x minus xi n and n এর factorial, and it can be written as so easy, that's e to the power lambda x minus xi. This is the iterated kernel. Not only iterated, this is the resolvent kernel from using iterated kernel. And if we write the solution, so f of a if phi of x equal to f of x, that means 1 plus lambda, that is 1 in here, 0 to x resolvent kernels, that means e to the power lambda x minus xi, and f of xi, that means 1, so d xi. So integrating with respect to xi, that's we will find a solution lambda x minus xi and divide it minus lambda. And this is limit 0 to x, only this where the lambda is 1, so putting these values we get this is 1, and the upper limit is x, then this is 0, so the lower limit is 0, then this is plus x. So when putting the upper limit, this is minus 1, and the lower limit 0 to x, so answer e to the power x. So e to the power x be the solution of the integral equation of this integral equation phi of x d of x, because host kernel is 1. So host kernel is 1 and f of x is 1, then the solution e to the power x of its. Thank you very much.